Okay, today we're going to start our conversation about electrochemistry. Electrochemical cells are super important to you guys. That battery that in your cell phone, that's an electrochemical cell. So all you people who have iPhones or are constantly looking for a charger, that's the electrochemical cell that's bleeding out on you. So electrochemistry is the study of the relationship between chemical potential energy and electrical energy. So you can have a galvanic cell. So this is what happens. Your cell phone is basically a galvanic cell, and the electrons can run your cell phone in that battery. Then at some point in time, your battery reaches equilibrium and it stops flowing, and then you would refer to your cell phone as dead, right? Then you go home and you plug it in and you basically turn it into an electrolytic cell because you're trying to recharge your battery. So study of this in battery science is nowhere it needs to be. And that's the problem with like electric cars. You've heard people complain about it. It's probably one of the reasons I don't have a Tesla. They're pretty cool. But the battery science is just not where it should be. So if you got into that, there'd be big bucks. So chemical reaction can produce electricity, or electrical energy can be used to carry out chemical reactions. That's the difference between a galvanic cell and an electrolytic cell. All of this occurs via the flow of electrons. So chemical reactions can generate electrical energy if they occur spontaneously. What's the sign of G when they occur spontaneously? It's a negative sign. So I've done this chemical reaction for you where I just take a piece of copper and I put it in a solution that is clear and colorless. If you weren't a chemist, you might think that it looked like water, but we never assume anything's water. So silver nitrate and copper added together. Copper is more reactive than silver. So copper wants to be part of the compound. Remember, everybody wants to be part of the compound. In this case, because copper is more reactive, this chemical reaction will happen, and it will happen spontaneously. Is this redox? Well, let's remind ourselves of our rules for assigning oxidation numbers. Remember, elements standing by themselves always have an oxidation state of 0. The other thing you can count on is that group 1 metals are always +1, group 2 metals are always +2, always. So those are rule 1 and 2 are always. In a compound, hydrogen is usually +1, but it could be with a group 1 metal, then it would be -1. The only oxidation states that are possible for hydrogen are +1 when it's a cation, 0 when it's elemental standing by itself, and -1 if it's an anion. Never give hydrogen any other oxidation states. Oxygen is usually -2, or unless it's a peroxide, then it's -1. So the total of the oxidation states of all elements involved in a compound will always add up to the charge on the ion, or 0 for a compound. So in this case, these are compounds. Silver nitrate is a compound. It has no charge because it's not an ion. So the silver plus the nitrogen plus the oxygen will add up to 0. So let's see. Let's assign oxidation numbers. Oxygen's -2. It usually is unless it's a peroxide. Nitrogen, that makes nitrogen +5 because silver is always +1. Silver is the one I see people make the most mistakes on. Silver is not +2. Silver is always a +1. Copper is standing by itself, so its oxidation state is 0. So remember, silver went from an oxidation state of +1 to 0. Did it do that by gaining or losing electrons? It gained electrons. Copper went from 0 to +1, so it lost electrons because it lost those negative charges. It's not going to produce electricity in this particular case because the electrons were exchanged directly between each other and the electrons did not have to migrate or travel between anything. Let's see what that looks like. So electrochemical cell requirements. You have to have 2 half cells containing aqueous solutions and electrodes. The electrodes can be either gases or usually pieces of metal. They need to be connected by a wire, so the electrodes will be connected by a wire, and that's where the electrons pass through. And then the center, there has to be a salt bridge. That's to maintain electrical neutrality. Electrons can't travel from one side to the other and then just end up with a buildup of negative charges on one side. That will not happen. So you have to have cations moving along with the electrons through what's called a salt bridge in order to even out the charge. So there's your qualifications in order to be a charge, in order to be an electrochemical cell. These are the things you need to have. So here's a picture of an electrochemical cell. Sometimes you see a single compartment with a barrier between it. Sometimes you see 2 separate compartments like such. So notice that the copper solution and the copper electrode are in the same cell. The zinc solution and the zinc electrode are in the same cell. That's because zinc is going to change oxidation states by losing electrons. So zinc is going to be a solid metal at the electrode. It's going to lose 2 electrons and then end up in the solution. So the concentration of the solution, the zinc ions, will increase. The electrons will go from the zinc cell over to the copper cell through that connection. So this is basically a diagram of that picture you see over to the left. Notice, take a close look at that picture. Do you see that there's no salt bridge that's going over? This is actually an extra special cell that keeps anything but cations from moving between the 2 cells. So the cations can move freely and nothing else. So the voltmeter measures the electrical current. When the cells reach equilibrium, the voltage is 0, no more electrical current. Think of dead battery. So we have electrodes. We're going to use solid electrodes for our purposes. The surface at which oxidation or reduction half reactions occur is what we're referring to when we say electrode. The anode is where oxidation occurs. So when we say oxidation, it's changing from a solid to being dissolved in a solution. The anode is the location for the oxidation half reaction. Notice that the vowels go together and the consonants go together. Reduction occurs at the cathode. That's the location for the reduction half reaction. So you might have been reminiscent of when we did oxidation numbers and balancing half reactions in the beginning of the year. So at the cathode, what will happen is the ions that are in solution will gain electrons and end up being solid metal. This is how you plate one metal with another metal. So it's actually big business to take cheap metals and plate them with expensive metals. You wouldn't want to have to buy, say, a kitchen faucet or something made from pure nickel. It would be too expensive. So all us people who aren't rich would just have cheap, crappy stuff without electrochemistry. So thank goodness we have a stupid memorization trick. The memorization trick is a fat red cat ate an ox. So the fat red cat, that stands for reduction at the cathode. And fat means that the cathode is going to get bigger. because there's going to be more metal deposited on it. Anox stands for the anode is where the oxidation occurs. And the oxidation, or where the ox is going to get smaller. So what that means is the anode is going to decrease in mass as the solid is losing electrons to become part of the solution. So just remember that fat red cat ate an ox. And that's got all the pieces of information that you need. So since the copper is the cathode, a fat red cat gains the mass. Where does the mass come from? The mass comes from Cu plus 2 gaining 2 electrons to make Cu0, or copper solid metal. So the concentration of Cu plus 2 ions decreases, the mass of the copper electrode increases. The zinc is at the anode where it's the anox, so it was eaten. So it's losing electrons and it's getting smaller. So the anode will actually decrease in mass. And zinc metal will lose 2 electrons, give them to copper, and he will turn from solid zinc metal to zinc floating in solution. So the mass of the zinc electrode will decrease and the concentration of the zinc ions will increase. Okay, is this reaction at equilibrium? The answer is no, because remember I told you the volts will be 0. You'll stop passing electrons once you're at equilibrium. So remember our fat red cat. So what's happening to the concentration of zinc 2 plus ions? Remember, the zinc electrode is solid zinc metal. Do you see it's getting smaller? So it's because the solid zinc metal is turning into zinc 2 plus, floating around in solution. It's the copper ions that concentration is decreasing because they're being deposited as copper solid. So here comes the $1,000,000 question. How do we know which electrode is which? Well, you've got to use a table to predict which electrode is the anode and which electrode is the cathode. So you guys, I gave you a chart. Let's look at that. I'm going to show you the way the chart's going to look. It's not going to look like what I gave you, but those are just notes. So the more negative in the table gets oxidized, anode, oxidation, electron donor. The more positive in the table gets reduced. Cathode is reduction, it's electron acceptor. So you see, the chart's not going to have the arrows on the side for you. But let's find a way to remember this. So we know that fluorine is the most electronegative. He is the best at taking electrons. So he is the bossiest element on the periodic table of the elements. So have that fact remind you that fluorine up there with the opportunity to take electrons, he's going to do it. So that tells you that the top there is the most likely to be reduced. The most electronegative means he's the most likely to be reduced, means that he's the best at taking electrons, means that in all circumstances he will be able to take electrons. So see how he's positive 2.87? That means that he is going to be reduced. Anybody else he comes in contact with is going to be oxidized. So here's what you do. You find the two substances that are involved in the chemical reaction. Once you find them, rank them. So put the one that is at the top of the reduction potential chart on the top, the one that is the bottom on the bottom. Then what you're going to do is the top guy, the one who's going to be reduced, stays as he is. The other guy, you're going to flip him because this is only reduction potentials. When you flip him, you change these reduction potentials to oxidation potentials, and you also have to change the sign. So this is the way a lot of these problems are going to work. You're going to label the anode and the cathode. So we're going to do between zinc and copper. So you find copper on your chart first. Why doesn't everybody circle copper on your chart and then circle zinc. What is the potential listed for copper 2 plus being reduced to copper solid? So it's 0.34. What about zinc? So negative 0.76. These are both reductions. This is a reduction potential chart. You can't have two reductions. You can't have a reduction without an oxidation. So what you're going to do is you're going to flip this and turn it into zinc metal losing 2 electrons to become oxidized. We change the sign of this like such. So this is out, and this is my overall reaction. Remember, you have to have the electrons balanced. Remember all the way back in first semester when we did balancing half reactions? And what is the overall potential is going to be 1.10 volts in the positive direction. Now, I'm going to tell you right now, I'm recording this because you're going to get to the point where you're like, wait, which way? What? Because this is anything that occurs both ways, and anything where zinc's going to sometimes be reduced and zinc's going to sometimes be oxidized can be confusing. So just remember, at the top with fluorine, we know he wants to gain electrons. At the bottom with lithium, we know that lithium wants to lose electrons. He doesn't want to do that. That's why it's negative 3.04. So you flip him around, all of a sudden he's positive 3.04 and he's being oxidized. That's what he wants to do. Metals want to lose electrons. Non-metals want to gain electrons. When you're comparing two metals, that's the confusing time. You just have to look, who is closer to fluorine? Whoever's closer to fluorine will be reduced. Fluorine wants to be reduced. The electrons are going to travel from the zinc to the copper. So that's the way the electrons will go. Now, this is the part that I always got backwards. The sodium has to go with the electrons in that salt bridge. So in this case, zinc's going to be losing electrons. So the mass of the zinc will decrease. Copper is going to be gaining electrons. So the mass of the copper electrode will increase. Zinc's going to be turning from zinc solid to zinc 2 plus ions. Therefore, the concentration of zinc ions will increase. On the other side, the concentration of the copper ions is going to decrease. So that's why you have to have that salt bridge. It'll shut down if you don't have the salt bridge to balance those charges out. So which one did you label as the anode? So remember our fat red cat ate an ox. So an ox tells you that at the anode, the oxidation occurs. At the cathode, the reduction occurs. So the electrons, if they're going from left to right, the electrons are going to go find those copper 2 plus ions, and they're going to make that fat red cat even fatter, which is copper. But just remember, the positive cations flow in the same direction as the electrons. The electrons flow from anode to cathode. An anode's the site of oxidation. It will be getting smaller. Cathode is the site of reduction, and it will be getting larger. What's wrong with this picture? No salt bridge. Not going to work. Ions cannot flow without a salt bridge. Therefore, electrons won't flow either because they can't just build up. We know that electrons can't just build up. We know that electricity does not flow without anywhere to go. Why don't you guys check yourself, test yourself. Look at your chart. Find aluminum +3 and lead +2. So which one is closer to fluorine? Lead. So what you're going to do is leave lead as it is. Then you're going to take aluminum and you're going to flip it. Fortunately, those E values in volts, you do not multiply them by the number of moles. Okay. So which one's going to be the anode? Which way will the electrons flow? Left to right or right to left?
Or right.
Remember, they stick with their buddies in the solutions. You have to have a solution of lead with the lead anode. You have to have a solution of aluminum with the aluminum anode. Aluminum is the anode, lead is the cathode. So which one will gain mass, aluminum or lead? Electrons are going to flow that way to turn the lead +2 ions into solid lead. That will make the mass of the lead cathode increase, and it will make the mass of the aluminum anode decrease. Like such. Remember, if you were balancing this, you'd have to have the same number of electrons. So you would multiply the aluminum by 2, the entire chemical reaction. The entire half reaction would be multiplied by 2, and the lead one would be multiplied by 3, and there'd actually be 6 electrons being transferred. Overall spontaneous reaction would be as such. Now you can get the reverse reaction to happen by plugging it in. And that's what you're doing when you go home tonight and you plug your cell phone in. So one more time, which electrode's losing mass? Aluminum. Because now the solid aluminum is aluminum +3 ions in solution. What's happening to the concentration of aluminum +3 ions? Increasing. This notation is supposedly not on the AP exam, but that doesn't mean you don't need to know it. Doesn't mean it's not going to be on a placement test. Doesn't mean it's not part of first year chemistry. They just don't write that. So they just separate the phase boundary with one line. They use 2 lines for the salt bridge, and electrons flow from anode to cathode. So this is where you get batteries. We use batteries all over the place. So here's some examples of some batteries that you have used all the time.